In this video, we will talk about standard scores. We will see how standard scores are calculated, what they represent, and why they are so useful. To motivate the idea of a standard score, let us look at some of our actual data. Let's go to Jamovi. Let us first load our data set. And let us look at some of our vocabulary scores. The first child listed here has a vocabulary score of 47. This means that the child answered 47 questions correctly or selected 47 pictures correctly. Okay, is that a good thing or a bad thing? Is that a good performance or a bad performance? This 47 is essentially meaningless unless we know what kids are expected to do with this test at this age. Let us see what the other kids in our small sample did. We'll go to Exploration, Descriptives, and choose to look at the mean, median, minimum, and maximum performance. So for vocabulary in kindergarten, we see that scores ranged between 38 and 91, and that a mean score was 61.3. So compared to 61.3, our score of 47 seems quite low. But how low is it really? What proportion of children scores higher or lower than 47? That would be a much more useful kind of information to understand the meaning of this 47. Let us look at the standard deviation for our sample. The standard deviation is 12.1. So our score of 47 is 47 minus 61.3. That is more than 14 points below the mean. And 14 points below the mean is more than one standard deviation. In fact, by dividing 14.3 by 12.1, it turns out that this child with the score of 47 correct choices is actually 1.18 standard deviations below the mean. What does that mean? To understand the proportion that is associated with this score, we can go to our normal probability display. So this is our normal probability display, and let us go to a score of minus 1.18. That is 1.18 standard deviations below the mean. This is where this child lies with respect to the normal distribution when we think about it in terms of standard deviations. And if we click up to, we see that 1.18 standard deviations below the mean is associated with the probability of about 12%. So this means that our child is at the 12th percentile. This means that 88% of children score higher, and 12% of children score at 47 or below. Indeed, if you go back to Jamovi and count how many of the vocabulary in kindergarten values are higher than 47, you will see that there is 42 of them. 42 out of 47 children in the sample is about 89%, which is exactly what we expected based on looking at the percentile from the normal distribution. So what we did by using information from the mean and standard deviation was to convert this meaningless raw score of 47 into a value that is directly interpretable as a proportion of children scoring higher. So we turned an almost useless number into a highly informative quantity that tells us how high or how low this child scores for this test and in comparison with the same age range, or at least in comparison with a relevant sample. This is the distribution of vocabulary raw scores in kindergarten for our entire sample of 47 children. Here is the histogram, and on top of the histogram, I have plotted a normal curve with the same mean and standard deviation as the sample for comparison. So it looks like the histogram is a fairly good approximation of this normal curve, although there seems to be a slight excess of children scoring between 50 and 60 compared to children scoring around 60. Anyway, let us use this sample to see how we go from the raw score values, which as we saw are essentially uninformative, to those values that are informative, that are interpretable as proportions of the relevant sample. Recall that the mean of this sample was 61.3 and the standard deviation was 12.1. So the first thing we do is we subtract the mean from each value. If we subtract 61.3 from each value, then we get to this histogram. Now, as you will notice, this is identical. Of course, the distribution of values hasn't changed. What has changed is that every value is 61.3 less than it used to be. So the dispersion is unchanged, and indeed, the new set of numbers has the same standard deviation as before. But since we subtracted the mean from every value, the mean is now 0, because a value that would be around 61 is now around 0 by subtracting 61.3. And the same is true for every value. So values that used to be around 61 are now around 0. It's like shifting the histogram so that the mean is now at 0. That's what subtracting the mean did. Let us now divide every value by the standard deviation. Again, it should not be a surprise that the histogram is identical. We did not change the relative standing of any number. We just divided every number by 12.1. The mean remains unchanged because it's not affected by the division. What used to be 0 is still 0. What did change was the actual values of the numbers, so that a number that used to be 12 points above the mean, which was about 1 standard deviation above the mean, well, divided by 12.1 is now around 1. So being 12 points above the mean is now being 1 above the mean. 1 standard deviation above the mean. Indeed, the numbers here are interpretable as how many standard deviations above or below the mean the original value was. And that's what a standard score is. So we have calculated standard scores, otherwise known as z-scores, using the formula raw score, which is our original measurement, minus the mean of all the measurements, divided by the standard deviation. And this is called a z-score or standard score. And a z-score is exactly a number that expresses how many standard deviations away from the mean the original measurement was. So a positive z-score means the original measurement was above the mean. A negative z-score means the original measurement was below the mean. The reason this is so useful is that if our data are approximately normally distributed or can be brought to be approximately normally distributed, then the number of standard deviations above or below the mean is directly linked to a probability because of the direct link of probabilities to positions in the normal distribution. And as you recall, probability is thought of as frequency or proportions, how often things happen on it, or in what proportion of instances things happen. So a probability of 12% is the same as a 12% proportion of the sample or of the population, depending on how things were computed. So by using a z-score through the normal distribution, we can link to percentiles the proportion of children scoring below and above our original raw score. And therefore, we have computed a very informative measure out of the raw score that tells us the relative standing of this child as a proportion of the sample. And that's what a z-score or standard score is and why it is so useful.